Hello friends, good afternoon and welcome to EduSat live lectures. Dear friends, today in thermodynamics we will be discussing about equilibrium thermodynamics properties. To discuss this topic we have with us our subject expert Dr. Amit Kumar. Dr. Kumar is Assistant Professor in Department of Chemistry in Dayal Singh College, University of Delhi. Without further ado, I would like to welcome Sir to our studios and request him to start the lecture. Welcome, sir.
Thank you so much. Dear viewers, first of all let me wish very good afternoon to all of you, and as you have been looking at the series of chemical thermodynamics, we have dealt with a number of topics, and the last lecture was devoted to the discussion of spontaneity and equilibrium, whereby we had discussed what way the criterias of spontaneity and equilibrium in terms of various thermodynamic properties could be derived, and we derived all such formulas. Now, on the basis of which we can predict the spontaneous change or the equilibrium process of a system. The change we envisage, whether it will be a spontaneous change or not, or the system will be at equilibrium, can be predicted depending upon the calculations which we had done using those formulas. So, in brief we would say that internal energy for any system for which entropy and volume is maintained under constant conditions, the energy of such systems should decrease for any change to be spontaneous in such systems, and should cease, that means the internal energy for such a system should not change under the condition that the system is maintained at equilibrium position. Having said this, there was another formula which were also discussed, that is the entropy change should be greater than 0 under condition of constant internal energy and volume. Apart from this, formulae were also derived for determination of spontaneity and equilibrium criteria under condition of constant temperature and volume and under condition of constant temperature and pressure. And we did observe that it further led to conceptualization of two important thermodynamic properties, the Helmholtz energy and the Gibbs energy. And it is the Helmholtz energy which becomes prevalent under temperature and volume constant conditions, whereas the Gibbs energy becomes important for consideration and subsequent determination of about the spontaneity or equilibrium condition of an envisaged change within a system, depending upon whether the Gibbs free energy for such a change within the system will decrease or will remain same. After that, we also discussed the Gibbs free energy of reaction. There let us have a look at once again what we had actually learnt. That is, Gibbs free energy change of a reaction. We considered three cases. Once, that the Gibbs free energy change for a reaction to be spontaneous should be a negative value. That means, in any given reaction, if we want that this reaction to be spontaneous, the Gibbs free energy of the reaction system should decrease, and that can happen. That can happen when the enthalpy change for such a reaction is a negative value, that means an exothermic reaction it is. Moreover, the entropy change for that reaction is also a positive value, that means the entropy should also increase in the reaction system. Such reactions are possible at all temperatures. Moreover, if the enthalpy consideration is not favoring the spontaneity of a reaction, it means if the reaction is not exothermic, if it is an endothermic, then such reactions are driven by entropy considerations and are called entropy driven reactions. On the other hand, if only reaction is an exothermic one, whereas the entropy decreases in such as the reaction progresses, and and the balance is such that the total Gibbs free energy change is negative because of that enthalpy change overpowers the entropy change factor. As a result, we can say such reactions are enthalpy driven reactions. Now, this is we considered about the conditions under which a reaction is spontaneous. Now, let us consider when a reaction can be at equilibrium. A reaction can be at equilibrium when delta Rg, that is the reaction Gibbs free energy of the reaction system, is 0. That means the Gibbs free energy within the reaction system does not change, and that can happen in a situation when delta Rh minus T delta Rs, which is the prevalent equation for Gibbs free energy change of a reaction, is equal to 0. It means the enthalpy change for that reaction should be having the equal magnitude compared to the T delta Rs factor, but opposite in sign, so that the net result is that delta Rg is 0, that is reaction Gibbs free energy for such a reaction is 0. Under that condition, we can say the reaction is at equilibrium. The reaction is at equilibrium means whatever is the equilibrium concentration of reactant and product species within the reaction mixture, that will remain same. That means practically the reactants would not transform to products, or the product side would also not convert to reactant species practically. So, such a state of system would be called as an equilibrium state, and the reaction would be called in the state of equilibrium. And from this we can also determine the equilibrium temperature. The idea is very simple, that Gibbs free energy delta Rg when is 0. So, it means delta Rh minus T delta Rs would also then be equal to 0, and therefore, delta Rh equal to T equilibrium delta Rs. And now, we can take this delta Rs factor to the denominator of delta Rh to get T equilibrium. So, therefore, T equilibrium is the equilibrium temperature for that specific reaction, that is equal to delta Rh by delta Rs. Similarly, this is the reaction system we have discussed here. Similarly, we can determine the equilibrium temperature for any physical process. For example, if suppose we want to determine boiling point of a liquid, we should have a knowledge of enthalpy of vaporization and entropy of vaporization for that vaporization process. So, since vaporization is concerned with boiling, so therefore, the equilibrium when a equilibrium is established between vapor pressure and the external pressure, then in that situation the temperature is known as boiling point, and therefore, equilibrium temperature is boiling point, that is given the symbol T subscript B. B means boiling. So, therefore, boiling temperature equal to just nothing but the ratio enthalpy of vaporization to entropy of vaporization. Now, so in a nutshell, we can say that what thermodynamics does for us in the prediction of chemical reactions. We should sum it up now. It describes the feasibility of a chemical reaction. You see, as we had discussed in the previous lecture, that for any reaction to be spontaneous, for it to proceed in forward direction to yield the products, the delta Rg of the reaction system should be a negative value. So, it means whenever for an envisaged reaction delta Rg, then Gibbs free energy of reaction is a negative value, then only the reaction will spontaneously occur. That is what spontaneous. I had also defined the meaning of spontaneity. Spontaneity means there is a possibility or feasibility of a chemical reaction or a physical process. So, when delta Rg is negative, it does mean that chemical reaction is feasible, or in other words, the chemical reaction is possible. That is what thermodynamic predicts. Whether a given chemical reaction will be driven spontaneously or is possible, in other words, or also can be said as is whether this reaction is feasible under the given conditions of temperature and pressure or not. That is what thermodynamics does for us. Now, I also gave another example that there is a lot of hydrogen and oxygen prevailing in atmosphere, and it is the atmospheric conditions which does not allow this reaction to be progressing at a rate at which we can we can perceive the formation of water in atmosphere. So, it means although the reaction thermodynamic predicts that the reaction is feasible, but thermodynamics never tell us how much is the time or the time frame which a particular reaction or a physical process will take for it to completion. So, therefore, thermodynamics, it does mean that cannot predict the rate of a chemical reaction or a physical process about which it describes whether this physical process or a chemical reaction is feasible or not. Now, question arises, if a reaction is feasible and if the rate of reaction is very slow, that practically we do not observe any reaction going on within the reaction system, then what should we do? So, does it mean that thermodynamics is of no sense to us, is making no sense? No, it is not. The fact of matter is, either you change the experimental conditions in order to enhance the rate of reaction. There are factors upon which the rate of a reaction depends. The rate of a reaction depends on temperature, for a gaseous system on pressure also. But now, there is another aspect which you can introduce. If you consider a reaction for which you observe that thermodynamics predicts because of delta Rg is negative and thermodynamic predicts that reaction is feasible and practically no reaction is been possible in your reaction system, then you can also enhance the rate of reaction by introduction of a catalyst system. Catalysts are those chemical species which enhances the rate of a chemical reaction. So, therefore, introduction of a catalyst is one way of carrying out those reactions which are not in a practical time frame, but thermodynamics predict them to be feasible. So, it is all about, we have considered that thermodynamic predicts whether a reaction is feasible or not. It also predicts whether a reaction system is at equilibrium or not. Moreover, in addition, it also predicts one more thing. What is that? That is, it also predicts that if you have envisaged a chemical change or for that matter a chemical reaction, and the thermodynamic consideration for the reaction such as enthalpy change of the reaction, that is delta RH, if it is a positive value, it means the reaction is endothermic, and moreover the delta RS is negative. That means the reaction which you have envisaged for this entropy of the reaction system does increase. Does decrease rather than an increase. What it does mean? Neither the entropy factor favors the reaction progression of a reaction, nor the enthalpy factor favors the progression of a reaction. Such a reaction therefore is an endergonic reaction, and that is those reactions for which delta Rg is a positive value, and such type of reactions are therefore prohibited reactions at all temperatures. So, the thermodynamic predicts these reactions of their own will never be possible, but I have also introduced the term of their own unaccompanied by any external agency. So, now question arises, can we do something to bring about those chemical reactions which thermodynamics says that they are of their own not feasible or not possible? So, the answer is yes. But before we discuss that, let me further say that for such prohibited reactions, no catalyst can be used for a thermodynamically prohibited reactions. If you use a catalyst system for a reaction, that can be used only for those reactions, only to enhance the rate of a reaction which the thermodynamic predicted to be feasible. So, catalyst even will not work anyhow for a reaction which is non-spontaneous, or thermodynamic predicts that they will not be possible. Now, the question arises, as I said, how to carry out such reactions. Now, these reactions can be carried out as coupled reactions. What is the meaning of a coupled reaction? If you remember, a couple of lectures back, we also discussed the coupled physical processes. For example, water which is lying on a tub on the ground floor cannot of its own can rise itself and can reach to the first floor. So, I said, but if you introduce a iron pipe into the tub, and then from one side two pipes you can introduce, and from one side you can exert pressure so that the tub is closed. In the closed vessel, when you exert pressure, this pressure can be used to let this water elevate in another pipe. That is the effect of pressure. So, what you have done is you have coupled the mechanical work which has been introduced on one pipe, one side, that has been used to raise the water level. That is, you are doing work to raise the potential energy of the system, and that is how the water which was of its own, for the water it was not possible of its own to rise to the first floor. But now, since you have coupled this process which is thermodynamically not feasible, non-spontaneous process, with a process which has exerted greater pressure, and the total process, the sum of total of two processes is for which delta Rg is negative, that physical process. So, these two processes when coupled together, they become possible. Similarly, if a reaction is there for which delta Rg is negative, that is, that reaction is feasible, and there is another reaction for which delta Rg is positive, that means thermodynamics says this reaction is not feasible. But when we couple the two reactions simultaneously, that means they are done simultaneously, the two reactions are done simultaneously, then in that situation, if the sum of delta Rg of reaction 1 and 2 is a negative value, it means in total, if we see in the reaction system, the Gibbs free energy in total decreases, then the reaction which was of its own was not feasible, now become feasible as a result of coupling with another feasible process, another physical chemical reaction which overpowered the Gibbs free energy consideration for a non-spontaneous chemical reaction. So, this is how by way of coupling non-spontaneous reaction with a spontaneous chemical reaction with greater delta Rg negative value, this is how we can let those reactions which are of their own not feasible, not possible, we can even carry out those reactions. An example we can give over here. You must have heard in your 12th standard biology textbook that glycolysis process. In the glycolysis process is just nothing but basically breakdown of glucose molecules to smaller molecules, and more important is the fact that in the glycolysis process the molecules for the energy requirement, that is adenosine triphosphate, gets generated. Now, just have a close look at what goes on in that reaction. Basically what happens is, one reaction is glucose molecule undergo combustion in presence of oxygen within each and every cell of the of any human or any other living organism. Then in that cell this combustion reaction occurs, and as a result of this combustion reaction carbon dioxide and water gets produced, and for which delta Rg for this reaction is minus 2870 kilojoule per mole. So, this is a huge amount of decrease in Gibbs free energy occurs as a result of this combustion reaction. Now, when you have 36 ADP molecules simultaneously, they combine with 36 inorganic phosphates and they make 36 adenosine triphosphate. From diphosphate, they each diphosphate adenosine diphosphate molecule take up an inorganic phosphate and do make up adenosine triphosphate, and also results in formation of 36 moles of water. So, water being a common chemical species in the two reactions, and for this reaction delta Rg, the change in Gibbs free energy is 1205 kilojoule per mole. Therefore, it does mean it requires the storage of free energy. Now, so it means that generation of these energy producing molecules is a thermodynamically non-spontaneous, non-favorable, but it occurs continuously in the cell. It is the energy requirement of every living being which comes through these ATPs only. So, this is continuously needs to be generated, but generation of these ATPs requires an increase in Gibbs free energy, and therefore, thermodynamic predicts this reaction to be non-spontaneous, not feasible. But when you couple it, you see the beauty of nature, how the nature has designed the living systems. It has coupled this energy producing molecule reaction which is non-spontaneous with with another reaction, that is combustion of glucose molecules within each and every cell of living system, for which delta Rg is highly negative, and the result is that when the two reactions are coupled, then the overall Gibbs free energy is sum of the two, and this is equal to minus 1665 kilojoule per mole. So, by way of coupling the two reactions, the generation of ATP, adenosine triphosphate molecules, become feasible process according to thermodynamics. So, this is how we can understand this naturally occurring mechanism of generation of ATP as a model for us to carry out those reactions which are non-spontaneous, but we can couple them with highly spontaneous reactions. Another example is metallurgical processes. In metallurgy, usually ores, oxide ores are reduced to give metals. For example, iron oxide ores are reduced to give iron metal, but in that chemical reaction is highly endergonic process, highly endergonic chemical reaction, that is delta Rg for this reaction is for the reduction of this metal oxide to metal is highly positive, that is delta Rg is a positive value, highly positive value. But then the fact of matter is, if you remember in your 10th standard, it is the coke that is carbon which undergoes combustion to form carbon monoxide there, which then couples with this reaction, and that is the burning of coke is an exergonic reaction. Delta Rg for that reaction is highly negative, and when the two reactions are coupled, so ultimately it leads to overall reaction for which delta Rg is negative, and that is how all metallurgical processes are possible. The metals which you acquire for your enormous number of day-to-day experiences, even in a room, so many objects made of metal are lying, they are obtained from these metallurgical processes, but this extraction of metals from their metal ores is a classic example of a non-spontaneous process which thermodynamic predicts of their own they cannot occur. So, therefore, you have learnt how to couple them with another reaction which is thermodynamically more favorable, which has one more common species, reacting species. So, therefore, this is how you can couple them and you can let them occur, and this is a most practical application of this knowledge towards the designing of such reactions. Right. So, we discussed there the criterias of equilibrium. Now, let us consider the classification of thermodynamic properties. So, what we have learnt till the point of time is that there are various thermodynamic properties. One are basically mechanical properties such as pressure, volume. These were state variables. I mean, some value could be assigned to them. So, pressure and volume were characteristic properties of system, and these were mechanical in nature. So, therefore, we would call them as mechanical properties. Then there are fundamental properties associated with the system, that is, temperature is a fundamental property. Internal energy, which was defined on the basis of concept of internal energy, was set up by first law of thermodynamics. Then there is entropy, the basis of conceptualization of entropy was the second law of thermodynamics. So, temperature, internal energy and entropy, all these are fundamental properties, of which temperature is a variable and internal energy and entropy is a conceptualized function of these variables. Right. Then there are some composite thermodynamic properties also. Composite means we have considered them as combination of more than one, that is two or more than two thermodynamic state functions. For example, enthalpy, which is a combination of internal energy and the pressure and the volume as state functions and variables. There is a Helmholtz energy. We have already seen that there is a Helmholtz energy can be considered as a sum of internal energy minus T temperature times entropy factor. So, Helmholtz energy is a combination of internal energy, temperature and entropy. Gibbs free energy again therefore is a combination of enthalpy, temperature and entropy. Alright. So, This was the classification of thermodynamic properties, how they are classified. They are being classified: mechanical properties, fundamental properties, and composite thermodynamic properties. Now question arises, does there exist some possibility of having some relationship between all these properties? Although we have been having various relationship, but the question arises, can we have working relationship in terms of differential equations so that we can look for more interpretation out of this? So therefore it is now the focus of our attention is to look for such properties. For that, let us consider a system. A system is subjected to condition, or in other words you can say restriction. Restriction means that it can only undergo expansion work. It can only undergo expansion work means it does mean that all the kind of work except for expansion work it cannot do. Now question arises, what is the meaning of this work other than expansion work? We have already seen what is the meaning of the expansion work. That is, mechanical work, whenever there occurs a change in volume of the system, then we say there is been mechanical work has occurred, or that work is itself called expansion work. Now what are the other kind of works? At some point of time I had used the word as electrical work, magnetic work, but what does actually it mean? What we mean by electrical work? Now let us consider a system. If you remember, in your 12th standard textbooks in electrochemistry section, you would have seen the example of Daniell cell. You would have studied it. In the Daniell cell, if you remember, a copper rod was introduced in a copper sulfate solution and a zinc rod was introduced in a zinc sulfate solution, and the two electrodes were brought to contact by virtue of a metallic wire. Moreover, the two solutions were further brought in contact with each other by virtue of a salt bridge or a porous plug, where the movement of ions would complete the circuit. Circuit means the charge flow. What we were doing in the Daniell cell? Basically we were doing oxidation reduction reaction. What was oxidation reduction reaction? That is, we were doing oxidation of zinc along with reduction of copper. But how we were doing that oxidation reduction? We had designed this cell in a way in our left compartment, when zinc metallic rod made of zinc was introduced in zinc sulfate solution, it was reversible to zinc ions. So we could imagine that zinc ion do come at the surface of the zinc electrode and then release their electrons, or in other words, zinc atoms from the metallic wire do release their electrons and go to the solution phase, and then that is how concentration of zinc ion would increase. But at that same instant, the ions once again would reach to the electrode and get neutralized. That is how the zinc electrode was reversible to zinc sulfate solution. Now similarly, copper metallic rod made of copper was also reversible to copper sulfate solution. Now when they are brought in contact, there occurs a flow of electrons. That is what we need to discuss. If we understand this aspect, then we would be able to understand what we mean by electrical work. So we study it in subsequent section. Thank you. Alright, so now we discuss that what way the work other than expansion work can be observed. So, we have considered that a cell, Daniell cell example, where we have basically a reaction in which for example, when a zinc granule is added in a copper sulfate solution. So, what happens is that copper gets deposited and zinc granule continuously decrease in its size, or in other words, zinc granule inside the zinc is there and its size gets shorter, and on its surface the copper gets deposited. So, this was just a reaction which actually just occurred. But now if we separate the reaction which was occurring in this process, what was going on? Basically, zinc was undergoing oxidation and copper was undergoing reduction. That is how this reaction, when we do in a Daniell cell, zinc electrode being dipped in a zinc sulfate solution, copper electrode being dipped in the copper sulfate solution, and the two are connected externally, as well as the two solutions are also connected in order to let the charge flow by virtue of movement of ions. Now, the circuit is complete. So, in that situation, what we have done actually, we have now carrying out the same reaction separately in two parts, one in which zinc is getting oxidized from metallic rod to the zinc solution, zinc ions are continuously increasing, and the counter ion, oppositely charged ion, negatively charged ions are being provided by the ions in the salt bridge. Similarly, copper ions from the solution side are actually getting deposited at copper electrode and they are getting discharged, and because negative ions are now accessed, so positively charged ion comes from salt bridge. So, therefore, in this way the migration of electronic species occurs externally in the external wire, and when electron movement is being brought about, that is charge flows, the charge flows means electricity is produced. So, this flow of charge can be hindered by virtue of some of the electrical objects. For example, electrical bulb can be introduced in the circuit which can glow. So, what we have let is the migration of electronic charge, we have facilitated for it to be used for our purpose, for our electrical purpose. So, what we are saying is, therefore, we have customized this reaction in order to obtain the electrical work. Electrical work means electronic movement can be harnessed to produce the electricity. That is what is the meaning of electrical work. Similarly, magnetic work we can deal with. So, therefore, all these are kind of works which we can put them to the use of the mankind for a specific purpose at hand, that is for generation of electricity, out of which we can do a lot many exercises, lot many processes. For example, electricity can do solve for us. So, therefore, it is our job to decide whether we want to harness some work out of a reaction going on, or we do not want to harness some work. That is our job, we need to decide it. So, all this the kind of, if suppose the zinc granule when was added in copper sulfate solution, there was a volume change. If you remember, the zinc granule, the size of zinc granule was decreased because zinc undergo depletion, and upon which copper was deposited. So, there was a volume change. That volume change was nothing but the work of expansion which actually occurred in that reaction. So, therefore, this reaction can be designed to either let it go on with expansion work, or you can design it along with expansion work, you can obtain some other kind of work other than expansion work. So, one example I did give you of the electrical work in this manner. So, you can put these chemical reactions into a code in order to obtain some other kind of work, for example, magnetic work too. So, which we can put them to use for specific purpose. So, these are called useful work. Now, consider the condition of equilibrium and fundamental equation. Now, our focus is basically to understand the relationship between different thermodynamic properties. So, for that I said that consider a system subjected to condition that it can undergo only expansion work. So, it means dW is basically a sum of dW expansion plus dWA work other than expansion. So, dWA is 0. So, you have only expansion work dW. Now, we will talk about this a little later now on. So, now consider condition of equilibrium or fundamental equation of thermodynamics. If you remember, we had derived fundamental equation of thermodynamics, and that is also called condition of equilibrium. That was very important equation which led to the conclusion of and consideration of entropy. So, therefore, ds entropy change equal to 1 by T du plus P by T dV. This was the fundamental equation of thermodynamics and is also called condition of equilibrium. So, now it can be redesigned in a way. We can take 1 by T common from right hand side, and that 1 by T which is being there on the right hand side can be introduced to the left hand side by multiplying with temperature on both sides. So, therefore, this equation get transformed to T ds equal to du plus P dV. Now, we can further rearrange it. We can take P dV to left side. What you get du equal to T ds minus P dV. So, this is just we have modified the fundamental equation in this manner in the form of equation 2, in which we can which says that internal energy change can be obtained if we know the, or in other words, we can relate the internal energy change with change in entropy and change in volume of the system. That is what we can obtain from this. So, we have modified this fundamental equation as given in equation 1 to an important one as change in internal energy in terms of change in entropy and change in volume. Now, we can design certain other such equations also. Let us now use definition of composite thermodynamic properties. What are composite thermodynamic properties? If you remember, enthalpy was one, and enthalpy is composed of internal energy and the pressure and the volume as state variables. So, now what we can do is we can again consider fundamental equation, the modified fundamental equation, which is du equal to T ds minus P dV, the equation 2. Now, in this equation, if you see that we further have H equal to U plus PV, we can that is equation 3, that is by definition the composite function enthalpy equal to U plus PV. Now, we can differentiate equation 3, what we get dH equal to du plus PdV plus VdP. So, now we can substitute the expression as obtained in equation 2 for du in equation 4. What you get is instead of du, when you substitute T ds minus P dV, so first two terms become our T ds minus P dV, then this term P dV also is written, and then VdP is also written. Now, minus P dV and plus P dV do cancel. So, what you have then is dH equal to T ds plus VdP. So, this is again another fundamental equation which relate the enthalpy change of a system with change in entropy and pressure. Now, can we look for the change in Helmholtz energy? Surely we can. Let us see how we can do that. Helmholtz energy is related to internal energy, temperature, entropy as A equal to U minus Ts. Now, we can differentiate this expression, and what we get we get dA equal to du minus Tds minus SDT. So, du, as you have already seen, which is the second equation, the first fundamental equation, the equation number 2, equal to Tds minus Pdv, which we had derived. So, we can substitute for expression of du in equation number 7. What we get is the first two term are Tds minus Pdv here, then there is minus Tds, this term is taken as such, and then minus SDT also. Now, again here we can see Tds and minus Tds, these two are same terms with the opposite signs, so they do cancel. What you get is change in Helmholtz energy dA equal to minus SDT minus Pdv. Now, the same treatment can be looked for Gibbs energy. Gibbs energy is again a composite function of enthalpy, temperature and entropy, and G equal to H minus Ts. And Again we can differentiate equation 6 G equal to H minus Ts. What you get? dG equal to dH minus TdS minus SdT. Now this has dH. So dH is basically du plus PdV plus VdP. So instead of dH we have in equation 10 we have substituted du plus PdV plus VdP. So it gave equation 11. Now in equation 11 you have du. Now equation 2 give TdS minus PdV as equivalent way of expressing du. So you can substitute du. Now in equation 11 what you get? TdS minus PdV for du, then plus PdV plus VdP as the resultant factors from dH minus TdS minus SdT as such. So this equation results. Now in this equation you can see TdS and minus TdS is there. So they do cancel, and PdV and minus PdV also are there. So they do also cancel. What you get is dG equal to minus SdT plus VdP. So now we have got this equation 12 as change in Gibbs energy is related to temperature change and pressure change. So ultimately basically what we have got is we have got 4 fundamental equations which we had modified the fundamental equation which was the basic fundamental equation of thermodynamics, that is ds equal to 1 by T du plus P by T dV, which we have modified by taking into account change in internal energy, change in enthalpy, change in Helmholtz energy and change in Gibbs energy. So what we get is these 4 expressions. These 4 are 4 different ways of looking at one fundamental equation, and these are also called as fundamental equations of thermodynamics. 4 fundamental equations of thermodynamics, which basically is relates the internal energy change with change in entropy and volume, enthalpy change with change in enthalpy with change in entropy and pressure, and Helmholtz energy with change in temperature and volume, and Gibbs energy with change in temperature and pressure. Now you can see this differential dG is equal to minus SdT plus VdP. So change in G is related to change in temperature and pressure. So what it does mean? That temperature and pressure are 2 natural independent variables for G. So G is function of 2 naturally independent variables, temperature and pressure. In same way, and in the same way, Helmholtz energy is a function of temperature and volume, and enthalpy is function of entropy and pressure, S and P, and internal energy a function of entropy and volume, S and V. Now having said this, these are 4 fundamental equations, and lot of algebraic manipulation has been done to derive these fundamental equations, and they are of much use because they help us to derive Maxwell relations, which are very important relations in thermodynamics. So therefore these equations are important. So the question arises, if these equations are important and a lot of mathematics is done to derive them, so how to memorize these equations, because it is very difficult to memorize these 4 equations. So for that there is a simplicity is been introduced in term of a thermodynamic square, a mnemonic diagram basically it is for, and is very useful for a number of thermodynamic relations. For example, let us consider G as a function of temperature pressure, A as function of temperature volume, H as function of entropy pressure, and U as function of entropy volume. So you should just need to know who is a function of what, that is Gibbs energy is function of temperature pressure, Helmholtz energy function of temperature volume, enthalpy function of entropy pressure, and internal energy function of entropy volume. So only 4 variables, temperature, pressure, volume and entropy, which are naturally independent, and depending upon them we have designed 4 functions: Gibbs energy, Helmholtz energy, internal energy and enthalpy. So you can just design a square. You can first write on the right side G at the center of one edge, then on another edge you can write A in the same order as I have written over here. Then you can write internal energy U, and then you can write enthalpy. So the order is a little different, H should be the last one and internal energy should be third. So now since G is function of temperature and pressure, so the naturally independent variable should be written at two corners, G at the center of edge and then two corners, one temperature, one pressure. And since A is function of temperature and volume, so one corner is occupied by temperature, so other corner would obviously be occupied by volume. Then internal energy we know is function of S and V, so V is already occupied by one corner, so S need to be occupied by another corner. So now another edge remains where we are left with only H, enthalpy, so we can just write at the center of the edge, and the two corners are pressure and entropy. Now question is how to write these four fundamental equations from this thermodynamic square. Once we just write this thermodynamic square, that can be written on the basis of just knowing who is a function of what. For example, Gibbs energy a function of temperature pressure, Helmholtz energy function of temperature volume, enthalpy function of entropy pressure, and internal energy function of entropy volume. So therefore, just knowing this information we can draw this thermodynamic square and now see how this thermodynamic square helps. Basically you may memorize that G comes to the right, A comes below, and opposite to A there is H, and therefore only left hand side where remains U, and who is a function of what helps you to just write at the corners which functions, which variable needs to be there. And moreover, two arrows pointing from top towards bottom diagonally needs to be introduced. So that is what this thermodynamic square is, which you should be able to write. Now if you want to write total differential of G, that is dG, so you just write dG there, and G for Gibbs free energy, since you can see from thermodynamic square that is function of temperature and pressure. So what you can do is you just write dt is dG equal to dt plus dP. Now you require the differential coefficient of dt and differential coefficient of dP. Now since t is one function, one variable whose differential you have written which is related to dG, so dt, now its differential coefficient you can get the opposite variable opposite to temperature is S, so you can just write S. Moreover, if from S the opposite variable the arrow points away, so a minus sign is introduced. If the arrow is pointing towards that, so a plus sign is introduced. For example, for P there is opposite direction arrow is been there, so VdP is been there. So dA, same way dA you can write dA, the A is function of temperature volume, so immediately you can write dt and dV. And moreover, in dt and dV you can see volume and temperature arrow is pointing towards them away from S and P, so therefore both ways minus sign you can introduce. Coming over to U has two variables S and V, so you can write ds and dV. From S the arrow is pointing away, so is plus sign, so towards V the arrow is pointing towards V, so is given minus sign. Coming over to H, from H you can see there is H is the only one where both the arrows are pointing away from its naturally independent variable. So dH in front of dH equal to sign, you can just write ds and dP, and their differential coefficients opposite to S is T, the arrow is pointing away from S, so is plus sign. There is dP, the pressure variable, opposite corner there is V volume, so you can write V here, and since arrow is pointing away from pressure, so is again given plus sign. So therefore in this way thermodynamic square helps you to memorize what way you can you need not mug up these equations, you can just by just knowing who is a function of what, just can write thermodynamic square. It helps you to just write all these four fundamental equations of thermodynamics. All these equations are just one or the other way of looking at same system. That's how you should be able to understand it. Now question arises, what information we can draw from these four fundamental equations? The answer is Maxwell's relation. What are Maxwell relations? Maxwell relationship basically are just nothing, but basically are a relationship which relate the change in experimentally determinable thermodynamic properties with change in theoretically determined thermodynamic properties. It means It relates the change in experimentally determined properties with the theoretical ones. So, you can experimentally determine the change in one of the properties. If it is related to conceptualized change, for example, enthalpy change, entropy change, Gibbs free energy change, Helmholtz energy change, so you can evaluate those properties. That is what is the role of Maxwell relations, and that is why these Maxwell relations are very, very important. So, now how these Maxwell relations, if they are so important, what are they and how they are derived? They are very simple to derive them. All you need to know is Euler reciprocity relationship. What is Euler reciprocity relationship? Just have a look at it. Suppose we have a function of two variables, that is x and y. Then if we want to write its total differential, we can write df equal to delta f by delta x into dx plus delta f by delta y into dy. So, df by dx, this is one of the partial differential coefficient of dx. df by dy is one of the partial differential coefficient of dy. So, since the differential coefficient, these are first derivative also. So, since the differential coefficient df by dx and df by dy are functions of x and y, are not they? Because f is a function of x and y. So, these differential coefficients, the first derivative would also be depending on x and y. So, therefore, df by dx and df by dy would also be a function of x and y. So, we can say just these differential coefficients as some other thermodynamic property. Let us say we call df by dx as m. So, m would again be a function of x and y, and suppose we say first derivative delta f by delta y is a function called n, which again be a function of x and y. Now, question arises, can we double differentiate them? Of course, we can. Suppose if we differentiate m, or in other words the first derivative delta f by delta x with respect to y now, and delta f by delta y with respect to x now, what we get is two second order differentials, which are they? Delta square f delta y delta x and delta square f delta x delta y. If f is a state function, these second order differentials, second derivatives should be equal. It means if f is a function of x and y, then the order of differentiation, when you consider the second order differential coefficient of f with respect to these two functions, the order of differentials are immaterial. So, but the question arises, isn't it m which is equal to del f by del x? Now, when you differentiate m with y at constant pressure, isn't it del square f by del y del x? And the opposite treatment if you do on del y by del x on n, then isn't it del square f by del x del y? If it is so, then what it does mean? That you can write df as not differential first order differential coefficient df by dx into dx, but you can write mxy dx plus nxy dy. Now, if you take double differential, it means you need to differentiate this m with respect to second derivative, that is y, that is del m by del y, keep x constant and then take n and differentiate it with respect to other one. The dx with respect to x you can differentiate it, keep y constant. So, since del m by del y and del n by del x these are just nothing but second order differentials. So, where just they are different from each other only in the order of differentiation by way of x and y. So, therefore, these two are also equal. So, it in a nutshell we can say Euler reciprocity relation help us to say that if we have a differential equation of the form of equation 15, that is dx equal to mxy dx plus nxy dy, then we should have delta m by delta y equal to delta n by delta x as a truth. This equation should be truthfully followed. This is true only when the equation 15, which is a differential equation, should be exact and f is a state function. So, now we can compare this equation 15 and we can apply this Euler reciprocity relation of the form to the all four fundamental equations. Now, isn't it this fundamental equation du equal to TdS minus PdV of the form of equation 15, which requires that df equal to m dx plus n dy. Now, n is now here minus p and m is here t. So, from this, if this is since internal energy is state function, its differential is an exact differential. So, this differential equation is an exact differential equation. So, therefore, we can say that by applying Euler reciprocity relation, that is the cross derivative should be equal, we get to observe that delta t by delta v at constant s, this s constant is equal to delta p by delta s at constant v. Similarly, from second fundamental equation of thermodynamics, that is equation 5, dH equal to TdS plus VdP, since again enthalpy is a state function and its differential is an exact differential. So, therefore, we can also apply Euler relationship to this equation 5, 8 and 12, all of these also. And what we get is, from 5 we get delta T, because T is here m, divide by this dP, that is delta T by delta P, keep the entropy constant ds 0. So, S constant here equal to delta V by delta S at constant P. Similarly, from equation 8 what you get, delta S by delta V at constant T equal to delta P by delta T at constant V. And from equation 12 what you get is minus delta S delta P constant T equal to delta V by delta T at constant P. So, these 4 equations, equation 17, equation 18, equation 19, equation 20, these are Maxwell relations. What they relate basically, isn't it that these first 2 equations relate what? They relate the under constant entropy condition, the rate of change of temperature with volume, that is the expansion coefficient basically we are talking about, with the change in entropy with change in pressure. And the second one relate the change in entropy with change in volume. Third one also does the same thing, but under constant temperature condition. Constant temperature volume condition equation 19 and constant temperature pressure condition equation 20. And if you remember, constant temperature volume condition, constant pressure and constant temperature condition, this was a very important equation for us. So, here we have just the expansion coefficient del V by del T constant P, just minus 1 by V is not introduced, is equal to delta S delta P constant T. So, equation 20 helps us to determine the change in entropy, how the change in entropy changes with change in pressure, just by knowing the expansion coefficient. And if you remember, when we had discussed the change in entropy with change in temperature and volume and temperature and pressure, we had derived these relations. So, that was a bigger way of deriving Maxwell relation and this is a shorter one. So, this way we come to the conclusion that Maxwell relations are very important ones and help us to determine equilibrium properties or various thermodynamic equilibrium properties that can be quantified using these Maxwell relations. So, with this we just say thank you very much for your patiently viewing our program. Thank you so much.
On that note, I would like to thank sir for this very interesting discussion, and I would like to thank you dear friends for watching our show. Stay tuned and keep watching. Thank you.